So good afternoon. My name is Dr. Richardson, and I will be the instructor for this course, An Introduction to Linear Algebra Using Python. My email address is listed below, srichards22@comcast.net, and this course is supported by the National Science Foundation Center for Integrated Quantum Materials under grant number DMR 12131319. So just some philosophical issues about this course. This course is intended for an audience of sophomore, junior level undergraduates who have no experience with either linear algebra nor Python. Purpose of this course is to show you that linear algebra is an extremely important topic that has broad applications in a number of fields: computational science, computational engineering, machine learning, artificial intelligence, and quantum computing. This course is entitled An Introduction to Linear Algebra Using Python. The course is not entitled An Introduction to Python Using Linear Algebra. So let me explain the difference. We're essentially going to discuss and go over lots of applications of linear algebra, and in the process, go over a small set of commands from Python, which is a general programming language which you can use to apply the concepts, and in the process, learn something about how Python works. Python is an extremely powerful language, and we're not going to cover all the possible commands that you can use in Python, but we'll get a taste for how Python works. So before we get started, some administrative points. I would say that it's important in this course to take notes. In particular, this course involves learning, and learning is not a passive activity. So by sitting back and watching me write on a whiteboard, you're not going to learn anything. Now, these lectures will be video recorded, and you'll have the capability of going back in time and look at them. But I think it's interesting that if you're looking at these notes, these lectures in real time, sit down and take notes. That forces you to, even if you look at the videos, that forces you to really make sure that you understand what's being discussed. There are problem sets for the course, as well as problem set solutions. You will learn nothing out of this course if you do not do the problem sets. First problem set for this lecture 1 is available on the Google Drive. I'll say something about that in a minute. And the solution key will be posted there also, and eventually copies of the video lectures. When you do a problem set, it's important not to wait until the day it's due. Now, I put a due date on the problem set, not with the understanding that you're actually going to physically hand in the problem set, but you should take about a week to do it. And just getting the problem set solutions and reading the solutions is really not a great way to learn anything. I prefer that you try to do as many of the problems as you can. And even when you get the solution key, don't look at the entire solution. Just take a piece of paper, cover the solution, and scroll down so that you can get some hints about where you might have gone wrong or where's a good place to start. Each problem set will also have a set of Python exercises, lab exercises. And the purpose of these lab exercises is really to teach you some of the concepts of Python, in particular, how to use these commands to learn linear algebra. And again, you won't get anything from the course in terms of appreciating what Python is and how to use it unless you do those exercises. And those are lab exercises. And there's really no reason to provide a solution key for them because they're pretty self-contained, most of them. Next thing I would say is I'd encourage you to ask questions. So after each lecture, there is a recitation section of about an hour. I'll be available to answer questions. I've also given you my email address. I'll give it to you again. S.Richards, starts with an S, ends with an S, 22 @Comcast.net, COMCAST.net. And I encourage you, if you have questions about the problem set, the lectures, problem set solutions, you see some typos in either the problem sets or the solutions or even the lectures, please communicate with me. I promise to get back to you within 24 hours of you sending me the email message. But this is a mechanism where I'm available to answer questions that you may have, and feel free to use it. Finally, you might want to get a ruler for this course, because both in working the problem sets and in going through the lecture notes, a ruler is going to be useful from time to time. So that's a good thing to have. Okay, so let's start. So one of the things that we want to do in linear algebra, one of the central tasks of linear algebra, is that we want to solve systems of linear equations simultaneously. Now, that's not all you can do in linear algebra, but that's going to be a major focus of this course. So if we're going to make any progress and figure out what that means, we probably need to ask the question, what is a linear equation? So what do we mean when we say we have a linear equation? So I will give you some examples. Here's an equation. X is an unknown, Y is an unknown. 3 and 7, excuse me, are numbers. That's an example of a linear equation. Here's another example of a linear equation. X divided by 2 minus Y plus 2 times Z equals minus 13. This equation has 3 unknowns, X, Y, and Z, and 1/2, minus 1, 2, and minus 13 are constants. Finally, X sub 1 plus X sub 2 plus X sub 3 plus ... plus X sub n equals 1. That is an example of a linear equation where there are n unknowns, X sub 1, X sub 2, X sub 3, etc. Okay, so to have this concept drilled in at a deeper level, probably should ask the question, what is not a linear equation? What's an example of an equation that's not linear? So for example, X plus 3Y squared equals 7 is not a linear equation. Y plus the sine of X equals 0 is not a linear equation. The square root of X sub 1 plus 2 times X sub 2 plus X sub 3 equals minus 13.9 is not a linear equation. So if you sit down and look at these 6 examples, there are some general rules that you can use or discern that'll tell you how to obtain a linear equation. So for an equation to be linear, all variables must appear to the first power. The second constraint that we have to meet is that all the variables in your equation do not appear as arguments of a whole class of special functions. They can't appear as arguments of exponentials or exponential functions. So they can't appear as arguments of exponential or trigonometric or logarithmic functions. So that example of sine x plus y equals 0 clearly doesn't meet that criterion. So it's not a linear equation. And third, the equation does not involve products or roots of variables. Okay, so all 6 of those equations can be viewed in terms of these 3 rules, and it's clear to decide which of those 6 are linear equations and which are not. So, how do we solve a system of linear equations simultaneously? And we'll probably get a little bit more space over here. Okay. So that's the central task at hand. So let's go through an example. So suppose we consider an equation that has x minus y equals 1 and 2x plus y equals 6. And the question we want to get an answer to is, what are x and y that satisfy both equations 1 and 2 at the same time? That's what we mean by simultaneous. Okay, so this is a problem you've seen before in your careers, primarily high school or earlier. And you could solve this problem by brute force. Namely, you could take equation 1 and you can multiply it by -2. And why we're doing this, we'll see in a minute. And then add the result to equation 2. So if you take 1 and multiply it by -2, then the first equation at least has a term that goes like minus 2x. If you add that new equation to equation 2, the terms containing x cancel out. So if you do this arithmetic, you'll get a new equation that says 3y equals minus 2 plus 6 equals 4, and you can solve that equation for y, and y is 4/3. Then the next thing you need to do is recognize that since you know what y is, if you plug it directly into equation 2, you'll get 2x plus 4/3 equals 6, and you can solve that easily for y, x, and you'll get 7/3. So at the end of the day, x is 7/3, y is 4/3, and there is a solution to this problem. And you should check it. You should take these two solutions and plug them into the original equations, 1 and 2, and see that everything is satisfied. Now, that's pretty straightforward and easy. But what about a set of, let's say, linear equations of 3 known variables, quantities, and 3 equations. So really 3 unknowns, sorry. So if you can imagine having a problem where you have 3 equations and 3 unknowns, the brute force method is going to get to be a little bit more complicated or tedious to deal with. So we need to come up with a general approach of solving systems of linear equations simultaneously. And we will do that by writing our 2 equations in a slightly bizarre form, the reason for which will become clear in a minute. So this is the general form of those 2 equations that I already solved previously. So before we get lost in any further calculations, why is this an interesting problem? Why should we even worry about having to solve a system of linear equations simultaneously? Well, we all use Google. We certainly use global positioning systems, the GPS. And in your studies as STEM majors, you have encountered and will encounter tons of science and engineering problems where this problem will come up. Well, you'll have a set of linear equations that you need to solve simultaneously. Okay, so some notation. X and Y are going to be variables. These are the unknowns. For reasons that'll be clear in a few minutes, A sub 1, 1, A sub 1, 2, A sub 2, 1, and A sub 2, 2 are going to be constants. And why I go through this trouble of introducing these subscripts 1, 1, 1, 2, 2, 1, 2, 2, we'll see momentarily. And the only other thing that's left in this problem are B1, B sub 1, and B sub 2, and these are constants. Okay, so the problem is, given 6 constants, find the 2 unknowns. But do it in a way that doesn't involve a brute force approach. So the first thing we're going to do in this approach, which we claim will be easier than the brute force scheme, is to find something called a matrix. And in particular, this is a specific matrix, which we'll call a coefficient matrix. We'll give it a name, A. And in the literature and in textbooks, it's an uppercase letter, which is usually written in boldface. It's going to be hard for me in lecture to keep this differentiating between bolded symbols and unbolded symbols. So what I will do is to define a matrix, I'll just use a capital letter from the alphabet with a tilde underneath. And 3 lines means is defined to be, so this is a definition. And I'm defining what I call, so these are matrices. This is a matrix. This is the name of a matrix. This is the name of a matrix. But now I need to tell you what the matrix actually is. The convention is to put it in parentheses, and it consists of objects called 1A11, 1A12, the other A21, the other A22. Now you can see where the subscripts come from. Matrices have rows. There's the first row, there's the second row, and matrices have columns. There's the first row, there's the second row. So if we look at this guy here, that is something which we will call a matrix element. It's an element of the matrix. And the 1, 1 subscript tells the audience that this thing lies, so this is, the first one is the row index that tells you what row the matrix element lies in. And the second subscript is the column index. It tells you which column this matrix element lies in. So for example, this thing here that I've circled in red, A sub 2, 2, is a matrix element that lies in the second row and the second column. A12 lies in the first row, second column. The matrix element A sub 2, 1 lies in the second row, first column. And again, the convention for a matrix element is that the first subscript has to be the row index. That's something we all have to agree on. And once we do that, then we know exactly what we all are doing. And the second subscript is the column index. This particular matrix that we've looked at again, I'll write it again. This matrix element is the first row, first column. This matrix element is the first row, second column. This matrix element is in the second row, first column. This matrix element is in the second row, second column. This matrix has 2 rows, 2 columns, and it's referred to as a 2 by 2 matrix. So when you write down a matrix, you have to tell the audience where the matrix elements are, or that's another way of telling the audience how many rows the matrix has and how many columns it has. Okay, so now that we have this matrix, this coefficient matrix, why is this coefficient matrix useful? What are we going to do with this? So let's return to the original problem. And I don't mind writing it again. The original problem is we want to solve this problem in general. A sub 1, 1 times x plus a sub 1, 2 times y equals b sub 1, and a sub 2, 1 times x plus a sub 2, 2 times y equals b sub 2. So we want to find x and y. I'll call this 1 and 2. So we're going to use the same procedure. It's just that we have to recognize what's going on in this particular case. Let's say we multiply equation 1 by minus a sub 2, 2, that matrix element. And then let's say we multiply equation 2 by the matrix element a sub 1, 2. And add the results. And this is something you should be able to do. You will find that that process will eliminate the y's, and you'll be able to get an exact solution for x. It'll be a sub 2, 2 times b sub 1 minus a sub 1, 2 times b sub 2 divided by a sub 1, 1 times a sub 2, 2 minus a sub 2, 1 times a sub 1, 2. And you should verify this. Pretty straightforward. So I've sort of outlined the process of how you solve for your unknowns. There's another unknown in the problem, that's y. I'm not going to write that out. I'm going to leave that to you, problem set 1, and you'll show that y will look like a sub 1, 1 times b sub 2 minus a sub 2, 1 times b sub 1 divided by a sub 1, 1 times a sub 2, 2 minus a sub 2, 1 times a sub 1, 2. So if you look at these two results, you see something interesting. Namely, this denominator is identical to this denominator and appears in both solutions. The numerators are different, but the denominators are the same. So we're going to have a very important definition in play at this time. We're going to define something called the determinant of A. And that's written by two vertical bars, and A, the matrix is inside. Sometimes people call this lowercase det of the matrix A. That's an alternate way to write the determinant. And the definition of this, so this is really definition. The definition of this denominator is a sub 1, 1 times a sub 2, 2 minus a sub 2, 1 times a sub 1, 2. Now, this is a definition, but it should not be an unknown creature to you, because in fact, in high school, you learned that if you have a matrix, let's say a sub 1, 1, a sub 1, 2, a sub 2, 1, a sub 2, 2, please get used to the idea of what these matrix elements are and where they should be. The first subscript is the row index, second subscript is the column index. So you saw in high school that in fact to calculate the determinant of this 2 by 2 matrix, all you do is multiply a sub 1, 1 times a sub 2, 2, according to this arrow, diagonal arrow, and you subtract from that a sub 1, 2 times a sub 2, 1. So it's curious that this definition that we came across to simplify our solutions to x and y is actually something that you can get by using this high school rule when you apply it to a 2 by 2 matrix. So we've discovered that x looks like In the numerator, again, it's a sub 2, 2, b sub 1 minus a sub 1, 2 times b sub 2. But in the denominator, you have the determinant of the matrix, the coefficient matrix A. For y, again, you have a numerator that's different. It's a sub 1, 1 times b sub 2 minus a sub 2, 1 times b sub 1 divided by the determinant of A. And if we're going to make any further progress, we ask, can we simplify these numerators? Here's a way of simplifying these numerators. So let me take the numerator for x. That's a sub 2, 2 times b sub 1 minus a sub 1, 2 times b sub 2. And if you think about this, this sort of looks like it could have the general form of a determinant, where you multiply this times this, and you subtract from that from and that times that. And the determinant that you would have to evaluate to get that solution has to look exactly like that square matrix, or the determinant of that square matrix. So b sub 1 times a, b sub 1 times a sub 2, 2 minus a sub 1, 2 times b sub 2. So it looks like the general form of the solution to x is the determinant of the coefficient matrix in the denominator. And the numerator, it looks like you're taking the determinant of the coefficient matrix, but not quite. You're taking the first column of the coefficient matrix, and you're replacing it by B1 and B2. Make that a little clearer. So here is what would be column 1. What should be there is A11 and A21, but you replace those guys, that's the first column, you replace the first column by the B1s and B2s. Now, you will show in problem set 2, or problem set 1, getting ahead of ourselves, that in fact y can be written as a solution that again has the determinant of the coefficient matrix in the denominator, and the numerator, you can guess what this trick is going to be. The numerator you obtain by taking the determinant of the coefficient matrix, but now you replace the second column of it by B1 and B2. And that's something that you'll show in problem set 1. So this discovery was made by Gabriel Cramer a while ago, 1750. And what we've discovered are, at least for the simple case of 2 unknowns and 2 equations, Cramer's rule. Okay. So this is nice. And it would be helpful to go through a simple example to see how all this connects and works. And we'll do that right now. And in fact, let us go back to the example that we did at the beginning of today's lecture. So we had 2 equations, 2 unknowns. x minus y equals 1, 2x plus y equals 6. And we're going to use Cramer's rule. We're not going to use the brute force approach, but we're going to use Cramer's rule to find x and y. So let's break this up into steps. First thing you have to do is find the coefficient matrix. A. That is always easy to do. Coefficient matrix just comes from going back and looking at the original two linear equations and reading off the coefficients. 1 multiplies x, minus 1 multiplies y. So the first row is going to look like that. Second row, 2 multiplies x and 1 multiplies y. So the second row is going to look like that. The next thing you have to do, so you can always determine the coefficient matrix by inspection. Next thing you have to do is identify B1 and B2. And that's easy. There they are. They're just 1 and 6. Just read them off. So far, not a lot of work. Third thing you have to do in Cramer's rule, or using Cramer's rule, is find the determinant of the coefficient matrix. So that's easy. The coefficient matrix, again, I'll rewrite it. It's this. So if you want to calculate its determinant, it's using the high school rule, 1 times 1 minus a minus 1 times 2. And so that's going to give you 1 plus 2 or 3. Okay. So we're in a position now to calculate x according to Cramer's rule. The denominator is going to have the determinant of the coefficient matrix in it. And the numerator is simply going to be the determinant of the coefficient matrix, where you replace the first column, C1, by B1 and B2. So since you already know the determinant of the coefficient matrix, you can write that down. And B1 and B2, you know what they are. So all you have to do is evaluate that determinant. I leave it up to you to show that that is, in fact, 7/3. And last step, what is y? Same process. It's the determinant of the coefficient matrix in the denominator. And the coefficient matrix in the numerator is, or the object that goes in the numerator is the determinant of the coefficient matrix A, where you replace the second row by B1 and B2. So the idea is in item 4, the first column. So in item 4, you replace the first column by B1 and B2. That stands for X. For item 5, you replace the second column by B1 and B2. A second column is associated with Y. And so that is this times this multiplied by 1/3, and you should verify that that's 4/3. So this is the same as we got before. You may argue that we got this solution in the same amount of time that we did using the brute force method, but that is going to change when you get to higher order problems. 3 equations, 3 unknowns, 4 equations, 4 unknowns, etc. And again, please, when you get a solution to a problem like this, please check the solutions. Go back and take these guys and plug them into the original equations to see that they satisfy everything. Now, the beauty of Cramer's rule comes when you try to apply it to more complicated problems. So again, I could write down the following equation, A, and I know exactly what these subscripts mean. a sub 1, 1 times x plus a sub 1, 2 times y plus a sub 1, 3 times z, that equals b sub 1. A sub 2, 1 times x plus a sub 2, 2 times y plus a sub 2, 3 times z equals b sub 2. And a sub 3, 1 times x plus a sub 3, 2 times y plus a sub 3, 3 times z equals b3. And let me clarify something here. So this is a sub 1, 3. So you can clearly see that. So you can use the brute force approach to show that, in fact, if you just go through the algebra, you will find that x has a numerator that goes like the following determinant, and it's a sub 1, 2, a sub 1, 3, a sub 2, 2, a sub 2, 3, a sub, let's see, a sub 3, 2, and a sub 3, 3. And again, this is going to be divided by the determinant of A, coefficient matrix. Y, again, you can show by brute force, is going to have a numerator that's complicated. Its denominator is still going to be the determinant of the coefficient matrix. And it's going to look like in the numerator, the determinant, where here are the matrix elements, A11, B1, A13, A21, B sub 2, A sub 2, 3, A sub 3, 1, B sub 3, A sub 3, 3. And again, you see the pattern. The first column is replaced by B1, B2, B3 of the coefficient matrix to get X. The second column of the coefficient matrix is replaced by B1, B2, B3 to get Y. These are things you discover when you do the calculation. And finally, Z, you can guess what she should look like, but I'll tell you what it is exactly. It is that. Note that the 6 matrix elements, 6 of the matrix elements are not changed. It's just the ones in the third column. And again, you divide this by the coefficient matrix, the determinant of the coefficient matrix. Okay. You will show that this is true by brute force in problem set 1. And I will say now there is a lot of algebra involved in this problem. I will say that this is probably the most complicated problem in terms of algebra that you'll work on in the entire course. And I will help you. I will spell out how you do at least 1/3 of the problem, and then I'll leave the rest for you. So I'll give you a guideline. Okay. So in all of this, we're still going to need to find out what the determinant is for a 3x3 matrix. You will find, again, in problem set 1, that will be a sub 1, 1 times a sub 2, 2 times a sub 3, 3 plus a sub 1, 2 times a sub 2, 3 times a sub 3, 1, 2 terms. You'll find a third term that looks like a sub 1, 3, a sub 2, 1 times a sub 1, 2, a sub 3, 2, sorry. Then you'll have a minus sign, a sub 1, 3, a sub 2, 2, a sub 3, 1, minus a sub 1, 2 times a sub 2, 1 times a sub 3, 3, And your sixth term will be your last term, a sub 1, 1 times a sub 2, 3 times a sub 3, 2. So you will show this. You'll derive this explicitly in problem set 1. By brute force, and it's pretty formidable in terms of algebra. But actually, there is a much easier way to remember this, again, using our rule from high school. First row, I have matrix elements a sub 1, 1, a sub 1, 2, a sub 1, 3, a sub 2, 1, a sub 2, 2, a sub 2, 3, a sub 3, 1, a sub 3, 2, a sub 3, 3. And to find its determinant, what you do is use that high school rule. You'll multiply. So this will be the determinant of A. And you'll get a term, a sub 1, 1 times a sub 2, 2 times a sub 3, 3. That's my first term. Then using my high school rule, I'll get a sub 1, 2 times a sub 2, 3 times a sub 3, 1. Then again, I'll get a sub 1, 3 times a sub 2, 1 times a sub 3, 2. You should note that you're getting exactly what you got before by brute force. And then the high school rule says go backwards, but you use minus signs. Minus a sub 1, 3 times a sub 2, 2 times a sub 3, 1. Minus a sub 1, 2 times a sub 2, 1 times a sub 3, 3. And then finally, a sub 1, 1 times a sub 2, 3 times a sub 3, 2. And I assure you, it's much easier to write down those 6 terms than to try to build them or construct them by brute force. Okay, so we're ready to go. So what we're going to do now is have a 5-minute pause where you can stretch your legs. It's 2:45, and we'll resume again at 2:50, roughly 5 minutes. Okay, so let's pick up from where we left off. So we now know how to set up Cramer's rule for a problem where you have 3 equations and 3 unknowns. And we also know 2 ways to determine the determinant, no pun intended, of a 3x3 matrix, one that has 3 rows and 3 columns. We can do it by brute force, which I give you as a problem to work on in problem set 1. Once you do it the first time, you never have to come back again. You believe it. Then I can you can always find the determinant of a 3x3 matrix using the high school rule. So let's go through an example of using Cramer's rule. Again, for a problem with 3 equations and 3 unknowns. So x plus y plus z equals 2. 2x minus y minus z equals 1. And x plus 2y minus z equals minus 3. And so we want to solve this using Cramer's rule. First thing we have to do is find the coefficient matrix, which again is always easy. You just look at the original equation you're given, and you can read that information off by inspection. First row, for example, the first equation, 1 multiplies x, 1 multiplies y, 1 multiplies z. So the first row of the coefficient matrix should look like that. Second row is 2 minus 1 minus 1. excuse me, third and final row is 2, 1, 2, minus 2. The next thing we're going to have to do to use Cramer's rule is we're going to have to find the determinant of A. Okay, so we know how to do that, but we need to be careful because there are a lot of terms, a lot of minus signs. So we're going to get 6 terms. Just using the high school rule starting out, we're going to get 1 times minus 1 times minus 1 plus 1 times minus 1 times 1 plus 1 times 2 times 2 minus, go backwards, 1 times minus 1 times 1 minus 1 times 2 times minus 1. And the last term, the 6th term, is minus 1 times minus 1 times 2. And you need to verify that that's correct. You can do the arithmetic. It'll come up to a result that gives you 9 for the determinant. Okay, so then you're ready. All you have to do now is solve for x. You have 1 over the determinant of the coefficient matrix, so that's 1 over 9. And then x, to solve for x, you take the first column of the coefficient matrix and you replace it by B1, B2, B3. So you're going to have 2, 1, minus 3 there. B1, B2, B3 are there. Same process we saw before for the problem of 2 equations and 2 unknowns. And the rest of the coefficient matrix is not changed at all, not altered. So now I have to do this, calculate this determinant carefully. And again, go slowly and write out all the terms. I have made mistakes in doing this. So you have to go slowly, especially get the arithmetic right and get the signs right. 2 times minus 1 times minus 1 plus 1 times minus 1 times minus 3. Let's continue over here. Plus 1 times 1 times 2 minus 3 times minus 1 times 1. These are the backward terms. Minus 1 times 1 times minus 1 minus 2 times minus 1 times 2. And you can do the arithmetic and you will find that this should equal 1. So 1 down, 2 to go. For y, again, I have 1 over the determinant of the coefficient matrix. And then what's in the numerator is the determinant of the coefficient matrix, but you replace the second column by B1, B2, B3. So in fact, in this case, you're going to have 1, 2, 1, minus plus 2, 1, minus 3, 1, minus 1, minus 1. That's the determinant you need to evaluate using your high school rule. So that's 1/9. You have, again, you may be proficient enough to do this in your head at warp speed. I'm not. Spell it out. Take the time. 1 times 1 times minus 1 plus 2 times minus 1 times 1 plus 1 times 2 times minus 3. Forward terms, backwards term, minus 1 times minus 1 times, 1 times 1 times 1 times the minus sign. I wrote it correctly. I didn't read it correctly. Minus 2 times 2 times minus 1 minus 1 times minus 1 times minus 3. You can do the arithmetic and you should get minus 1. Let's see, 2 down, 1 to go. So Z is going to be 1/9, and 9 comes from the determinant of the coefficient matrix. You take in the numerator of the coefficient matrix and you replace the third column by B1, B2, and B3 respectively, and the other 6 matrix elements are left alone of the coefficient matrix. So it's a completely different determinant to do. So what is it? Again, our high school rule tells us you have 1 times -1 times -3 plus 1 times 1 times 1 plus 2. Continue this over here. 2 times 2 times 2 minus 2 times -1 times 1. So my fourth term has a negative sign because I'm going backwards. 4 down, 2 to go. Minus 1 times 2 times -3 minus 1 times 1 times 2. And you can evaluate this, excuse me, and it turns out to be equal to 2. So in fact, for this problem, x, y, z are 1, -1, and 2 respectively. And again, I leave it up to you. So a solution exists, but you should check this. And the way to check this is just go back and take these values for x, y, and z, plug them into the original linear algebraic equations, and that'll show that those 3 variables, or the 3 values for those 3 variables, simultaneously solve all 3 of those equations. Okay. So Cramer's rule is nice, but there's a problem. The problem is, if you have a problem to solve where you have 4 linear equations and 4 unknowns, then you might think that, oh, okay, I'm just going to have to calculate determinants, and I know how to calculate the determinant of a 4x4 matrix. So if you take a 4x4 matrix and use your high school rule, you will see that you'll have 8 terms in your expression for the determinant. And you may say, oh, great, I'm good to go. Problem is that if you go back and solve, and I'm not suggesting you do this because I already had you go through the trauma of looking at a 3x3 case in problem set 1, but if you go through the brute force approach of solving 4 equations, 4 general equations, and with 4 unknowns, you will discover that you don't get 8 terms, you get 24 terms. So the message here is this high school method which you may have seen, should have seen, and memorized. What I'm trying to convince you is it comes from the algebra in solving those 2 linear equations simultaneously and 3 linear equations simultaneously. Okay? But this high school approach only works for matrices that have 2 rows and 2 columns, matrices that have 3 rows and 3 columns, and it fails miserably for problems where you have a matrix that has 4 rows and 4 columns. So if we're going to make any progress, we need to be able to treat higher order determinants. And there is a way to do this. It's called the method of cofactors and minors. Okay. So how does this work? Well, we have gone through two approaches to calculate the determinant of a 3x3 matrix in principle. We've used the high school rule, and I've suggested by brute force in problem set 1, you can show that the determinant of a 3x3 matrix has 6 terms: a sub 1 1 times a sub 2 2 times a sub 3 3 plus a sub 1 2 times a sub 2 3 times a sub 3 1 plus a sub 1 3 times a sub 2 1 times a sub 3 2. And I have my 3 remaining terms that I have a minus sign due to the fact I'm going backwards: a sub 1 3 times a sub 2 2 times a sub 3 1. Then I have a minus a sub 1 2 times a sub 2 1 times a sub 3 3. 5 down, 1 to go. And finally, I have an a sub 2 3 times a sub 3 2 times a sub 1 1. And again, remember, all of this came from writing down the general form for a 3x3 matrix. First row, second row, here are the matrix elements. You got to get used to this notation and being comfortable in writing down a general matrix of order 3. That means it has 3 rows and 3 columns, and writing down all the 3 matrix elements correctly. So I would like to come up with a simpler expression, if you will, or I'd like to rewrite this guy. So one of the things I'm going to do is let us recast or rewrite the determinant of A, and let's do it along row 1. So I'm going to take this original expression here, 3 stars, and rewrite it. I'm going to factor out A11. I'm going to factor out, for reasons we'll see in a minute, not just A12, but a sub 1 2, but a minus a sub 1 2. And then I'm going to factor out an a sub 1 3. So this is just algebra. And what I'm left are terms inside parentheses: a sub 2 2, a sub 3 3, minus a sub 2 3 times a sub 3 2. The second term is going to involve a sub 2 1 times a sub 3 3 minus a sub 2 3 times a sub 3 1. And then my third and final term is going to look like a sub 2 1 times a sub 3 2 minus a sub 2 2 times a sub 3 1. And so you need to check the algebra. But this is just an algebraic way of rewriting something that we already know. So I am going to call these guys terms. Excuse me. So there's term 1, excuse me, term 2, and term 3. Excuse me. And let me see if I can simplify each one of those terms. So term 1 is going to look like A11 times A22 times A33 minus A23 times A32. Now this guy inside the parentheses, it sort of looks like it has the structure of the determinant of a 2x2 matrix, but we don't know what the matrix elements are. And we don't know if it's actually the determinant or not. So we need some help. So the help is to go back and look at the original general 3x3 matrix. There she is. So now let's study this guy in parentheses. It involves multiplying a sub 2, 2 times a sub 3, 3. Well, that's just that times that. And then it has a minus sign, a sub 2, 3 times a sub 3, 2. Well, that's just that. So it looks like what this guy in parentheses is the determinant of a matrix that you get from the original coefficient once you get rid of the first column and the first row. So we are going to define this determinant as M sub 1, 1. We're going to give this thing a name. It's called the minor. And it's simply just this determinant. It's exactly what gives you what's in the parentheses. Okay. So our first term in that expression for the determinant of the coefficient matrix A is A11 times the minor of M11. This is a definition. And there's no accident, folks, that those subscripts are identical. Now, how about the second term? The second term looks like a minus, and you'll see why I made that algebraically. I made the algebraic choice of bringing out a minus 1 there. So the second term is going to look like minus a sub 1, 2 times a beast in parentheses. He is a sub 2, 1 times a sub 3, 3 minus a sub 2, 3 times a sub 3, 1. And the question we want to ask is, well, what is this guy? Is it also a determinant? Well, I don't know. But let's at least go back to the original coefficient matrix. There's the first row. There's the second row. There's the third row. And let's see what's going on. Here, I'm multiplying a sub 2, 1 times a sub 3, 3. Let's clean that up a little bit. Yeah. So that's a sub 3, 3. So I'm multiplying that to get the first term, and then I'm subtracting from that a sub 2, 3 from a sub 3, 1. So it looks like to get this creature in parentheses, I have to strike out the first row and the second column, and then I'm left with a matrix whose determinant I need to take. And that matrix is, again, a minor, but it has subscripts because the subscripts tell you which row you have to kill and which column you have to kill from the original coefficient matrix to get the desired result. And that's going to be a sub 2, 1, a sub 2, 3, a sub 3, 1, a sub 3, 3. So the second term is going to be minus a sub 1, 2 times the minor m sub 1, 2. And again, it's no accident those subscripts are identical. So you can see the game we're playing now. So let's look at the third and final term. It has x a sub 1, 3, and you multiply that by a sub 2, 1 times 3 sub 2 inside of parentheses, then a minus sign a sub 2, 2 times a sub 3, 1. And the game is, what is this guy? What's this guy in parentheses? Go back to the original coefficient matrix. First row, A11, A12, A13. Second row, A21, A22, A23. Third row, A31, A32, A33. And again, what's happening? Well, this tells me I have to multiply a sub 2, 1 times 3a sub 3, 2, and subtract from it a sub 2, 2 times a sub 3, 1. So in fact, what I have to do is go back to my original coefficient matrix, strike out the first row and the third column. I'm left with a matrix whose determinant I need to find, or I'm left with the following minor. Minor means less than, so you get an object that's less than the size of the original matrix. So the minor specifically is this determinant, a sub 2, 1, a sub 2, 2, a sub 3, 1, a sub 3, 2. So my third term is going to be a sub 1, 3 times the minor m sub 1, 3. So let us put all of this together. And what we've discovered is you can write down a new expression for the determinant of the coefficient matrix for the case where the coefficient matrix has 3 rows, 3 columns. And for the specific case where we're looking at doing this expansion over the first row of the coefficient matrix. So I have coefficients a sub 1, 1 times the minor m1, 1. I have a minus sign. I have a coefficient a sub 1, 2 times the minor m sub 1, 2. And I have a coefficient a sub 1, 3 times the minor m sub 1, 3. There is a clever way to simplify this even further. I'm going to put in here the number 1, but recognize another way to write number 1 is just minus 1 to the 1 plus 1 power. So big deal, why am I doing that? Well, it's useful here because if I take minus 1 and raise it to the 1 plus 2 power, the sum of those two, as indicated by the subscripts of the matrix element here, I get a minus 1, and that's this minus sign. And I still have the same minor, m sub 1, 2. And in my third term is going to look like a sub 1, 3 times minus 1, again, raise it to the sum of 1 plus 3. That's going to give me a positive sign. And now I can simplify these guys even further. I can write this as a sub 1, 1 times capital A sub 1, 1 plus a sub 1, 2 times capital A sub 1, 2 plus a sub 1, 3 times capital A sub 1, 3. And this is so important that it demands a box of its own. So I need some definitions here. I will call a sub 1, 1, a sub 1, 2, and a sub 1, 3 cofactors. These are not matrix elements. That's important. So the way I can distinguish between the two, matrix elements are lowercase letters and cofactors are uppercase letters. And a general expression for a cofactor, a sub ij, is that it's minus 1 raised to the sum of I and j times the minor m sub ij. So this is a cofactor, capital A, and the minor is indicated by the capital M. And so what is a minor? A minor is the determinant obtained from the original coefficient matrix A by deleting the ith row and the jth column. And that is, in all its glory, the method of cofactors and minors. And again, anytime we go through or introduce a new concept, it's always important to go through an example, and I will do that. So suppose you have the following matrix. Remember, the method of cofactors and minors is simply a way to find the determinant. And actually, it's a way to take a problem, in this case, of a matrix that has 3 rows and 3 columns, and you have to determine the determinant of that, but recast it into a simpler problem where you just have to calculate the determinants of matrices, minors, that are smaller, that have 2 rows and 2 columns. Okay, so let's use the method of cofactors and minors to find the determinant of A without going through the brute force method. Okay, first things first. First thing you have to do is let us expand. So you have to make a choice. Let's expand our determinant of A about something. And we're going to expand it about row 1. We'll come back to this later, but it's clear that you have at least, well, exactly 6 different expansions you could use. So there's 6 different ways to solve this problem. You could expand around any one of the 3 columns or any one of the 3 rows. So let's just do it for row 1. And you'll get to explore this and become more comfortable with this in problem set 1. Okay, first things first. So that means that the determinant of A using the method of cofactors and minors over row 1 is A sub 1, 1 times the cofactor A sub 1, 1 times the matrix element A sub 1, 2 times the cofactor A sub 1, 2 plus the matrix element 1, 3 times the cofactor A sub 1, 3. Okay, what's A sub 1, 1? By inspection, it's just 2. What is the cofactor A sub 1, 1? Well, by definition, it's minus 1 raised to the 1 plus 1 power times the minor A of M sub 1, 1. What is the minor M sub 1, 1? You go back to the original matrix A, you strike out the first row, the second column, and then you're left with a 2 by 2 matrix, and you take its determinant. And you should verify that that is exactly what you get when you strike out the first row and second column from the coefficient matrix. This is a straightforward determinant to evaluate. It's 1. So that means that A sub 1, 1, the matrix element A sub 1, 1 times the cofactor A sub 1, 1 is 2 times minus 1 to the 1 plus 1 power times the minor 1, and that equals 2. 1 down, 2 to go. What is A12, the matrix element A12 times the cofactor A12? In other words, what's the second term? Same story. I need to find A sub 1, 2, that matrix element. By inspection of the original coefficient matrix, it's minus 1. By definition, the cofactor A sub 1, 2 is minus 1 raised to the 1 plus 2 power times the minor M sub 1, 2. The minor is the matrix that you'll get by going to the original matrix, the original coefficient matrix, striking out the first row and the second column. If you do that correctly, you'll find the following 2 by 2 matrix, whose determinant is easy to evaluate. So A sub 1, 2 times the cofactor a sub 1, 2 is minus 1. That's what a sub 1, 2 is, times minus 1 to the 1 plus 2 power times 2. And you get a minus sign times a minus sign times a minus sign times a minus sign. That's a positive 1. So this all equals 2. Okay, one last term to evaluate, and then we're finished. The matrix element a sub 1, 3 times the cofactor a sub 1, 3. I have to figure out what the matrix element a sub 1, 3 is. It's just plus 1. I now have to evaluate the cofactor a sub 1, 3. It, by definition, is minus 1 raised to the 1 plus 3 power times the minor m sub 1, 3. Again, the minor m sub 1, 3 is obtained by going to the original coefficient matrix, striking out the first row and the third column, and you're left with a 2x2 matrix whose determinant you have to evaluate. Please go through these steps to make sure that you verify that, in fact, that is the right minor. So that's a relatively easy determinant to calculate, and so you're finished. The determinant of A is just A11 times the cofactor A11 plus A sub 1, 2 times the cofactor A sub 1, 2 plus A sub 1, 3 times the cofactor A sub 1, 3. And what we have discovered is, in this example, this is 2, first term is 2, second term is 2, third term is minus 6. Let's go back. Yep, 2, 2, minus 6. And that all simplifies to minus 2. Now, this problem, or this approach, is not unique. In other words, I could expand the determinant of A. Here I did the expansion about row 1. I just picked that. I invite you, and you'll do this on the problem set, but no, I mean, I actually invite you to do this because this is the only way to make sure you see what's going on. To do this calculation again, but do the expansion about row 3. Do the expansion over row 4, or row 3. Sorry, row 1, row 2, and row 3. And you'll discover, if you do the determinants right, you calculate the minors correctly, which is to say you calculate the cofactors correctly, and you use the right matrix elements for row 1, row 2, row 3, you should get the same answer. And similarly, if you expand about column 1 or column 2 or column 3 for that matter, you'll also get the same answer. So what's the big deal? Why do you want to have a method that gives you multiple means of approach, multiple ways to approach it? Well, I'll give you an example. Suppose you want to use the method of cofactors in minors to evaluate the determinant of this matrix T. And in principle, there are 6 different ways to do this. Well, if you look at this matrix, you should realize that in fact, there are 2 ways that allow you to do less work than the other 4. If you expand either about row 1 or column, row 1 or column 2, not column 1 but column 2, you're going to get a 0 matrix element here. The 1, 2 matrix element is 0. That's going to kill any contribution you have. So it's less number of terms to worry about. If you did the expansion around row 2, for example, you don't have any zeros. And so you're going to have 3 distinct terms you're going to have to evaluate. Similarly, suppose you have the matrix G. And so suppose the matrix G looked like this. Again, this is a matrix. So let's say G looks like, I don't know. I'm just pulling a matrix out of my head. Pi, let's say 7.5, let's say -1. So here is row 1, here's row 2, here's row 3. Here's column 1, here's column 2, here's column 3. The easiest way to use the method of cofactors and minors in this particular problem is to expand the determinant of G about column 1. Why? Because there are zeros here. And that means at the end of the day, you're only going to have to evaluate, instead of 3 terms, you're just going to have to evaluate 1. So that's going to save you some work. There are some cofactors you don't even have to go through the exercise of calculating, or minors that you don't have to go through the exercise of calculating, because those zeros will cancel those out. Okay, so I am in lecture 2 going to discuss some more examples of the method of cofactors and minors. But let me just say something about what your tasks are. So I'm finished. So your task, really to appreciate and get something out of this course, which I want you to do, is I want you to review these lectures. If you're taking this course in real time, you have the written lectures in front of you. If you're taking it by looking at a recording, I want you to look at the recording, and as you follow the recording, take notes and follow those notes. There are times in the lecture where I ask you to make a digression and to prove something to yourself. Do that. The next thing I need for you to do, if this is going to be a valuable experiment, is you need to do the problem sets. And again, I give you about a week to do them, so that's ample time. And the problem sets come in 2 parts. There are analytical problems that you need to work through and solve, typically 6, 7, or 8 problems. And they involve sitting down and doing calculations. And sometimes doing some algebraic manipulations, as you'll see in problem set 1. And again, the solution keys will be available to you, but you will get nothing out of this course if you just simply wait till the solution key is available and read it and try to work backwards. The way to do it is work on the problem. Then when you get a solution, check the problem set solution. And if you're stuck, then consult the problem set solution by just highlighting the problem set solution line by line. Use a covered sheet of paper and just go scroll down. So that's the only way you're going to learn what you're doing. You'll get hints as to how to go if you're really stuck. Second part of the problem set involves going through Python lab exercises. And here, these are exercises that are meant for you to do. So in the first problem set, I assume you know nothing about Anaconda, nothing about Jupyter Notebooks, nothing about Python, nothing about NumPy, nothing about SymPy, et cetera, et cetera, et cetera. The first problem set will get you started on importing Python on your platform, be it, excuse me, Mac OS 10, be it Microsoft operating system, or be it Linux. And then you need to work these problems and exercises because you're learning a new language. Python is a very popular, very powerful programming language. There are other languages that you could use to learn how linear algebra works. Unfortunately, they're not free. MATLAB was designed specifically to do matrix algebra, but it's not free. And not everybody has access to it. Same thing with Mathematica. So go through the exercises. The third thing I remind you is that you need to ask questions. So you have my email address, srichards22@comcast.net. Whether you view the lectures in real time or look at them as taped exercises, you should take the time to recognize that if you get stuck either in the lecture material, either the problem sets or the problem set solutions, you have questions, you determine that there are typographical errors or things that need more clarification, simply write me an email message and I'll respond to you within 24 hours. The other mechanics in terms of homework that I want to talk about is, for the moment, if you're a registered student for this course, you will be getting information on how to access the problem sets and problem set solutions. As well as video recordings of the lectures. And it turns out at some point in the distant future, but not too distant future, even if you're not registered for this course, we will put it online, available as a playlist on YouTube. And so it'll be available for the public at large. Okay, well, thank you very much for your attention. A week from now, we'll look at lecture 2, where we will do some more problems, more exercises, more examples of how the method of cofactors and minors works. And then we'll realize that we need to sit down and see where we are, and we'll discover that Cramer's rule can do a lot of great things, but it can't do everything in terms of solving systems of linear equations. And we will have to look at a completely different way of looking at this problem, so-called Gauss-Jordan elimination. Thank you very much.